What is the product of all real numbers x such that the distance on the number line between log x to the base 6 and log 9 to the base 6 is twice the distance on the number line between log 10 to the base 6 and 1? Placed in an equation, this would basically be log 9 to the base 6 minus log x to the base 6 is equal to twice the distance between log 10 to the base 6 and 1. Now, this is only true if x is less than 9, right? Because if x is less than 9, then this part becomes positive. Now, we have to eventually deal with the other scenario where x is greater than 9, and I will, but first let's just do this one. So using log rules, this will basically be 2 log 10, and I'm not doing anything fancy now. This is just basic log rules. Log 6 to the base 6, I just converted that guy. And then you guys all know that rule where you combine it. If they have the same base, it would be 10 over 6 to the base 6. And then, let's see, what can I do? I can combine this side over here. That's going to be the log of 9 over x to the base 6. And then this is going to be log 10 over 6 squared, using, again, a log rule. And I think that's about as far as we can go. Now, since they both have the same bases, we can deduce that 9 over x is the same as 10 over 6 squared. Right. Okay, so this should be fairly easy to solve, I think. Let's see here. What am I going to do here? 100 over 36 is 9 over x, and I guess we just cross multiply. So 9 times 36, which is 324, is 100x, and therefore x is equal to 3.24. Okay, so we got one value. Now our next scenario is pretty much identical to what I just did. The only thing is now we have to look at the scenario when x is greater than 9. Yeah. Okay, so if x is greater than 9, then it's pretty much the same. It's just reversed. Now it's log x to the base 6 minus log, 9 to the base 6. And that is equal to what we had before, which is the log. I'm just going to write the simplified version because it's pretty much identical. And then this combines. This time it becomes x over 9 to the base 6, and this is log of 6, 10 over 6 squared. Okay, so same as before, and now x over 9 is 100 over 36. So 36x is 900, and therefore x is 25. So I think what they wanted was what? The product or something? Yeah, the product of all the real numbers. Okay, so we had this one and this one, so we have to multiply them. So 3.24 times 25, and that is, I believe, 81. So 81 is the answer. That would mean E for number 11. Let M be the midpoint of AB in the regular tetrahedron ABCD. What is the cos of angle CMD? All right, so let's first attempt to draw a regular tetrahedron, and then we'll take it from there. Okay, so something like this, right? Here's your regular tetrahedron. Regular just means that all the sides are the same. So I'll just label this ABC, and then we'll call that one D, and then we'll call the side length X. And then what do they want? CMD. Okay, so CM, oh, where's M? M is the midpoint of AB. Oh, okay, so this is M approximately, right there. So CMD, I guess, is CMD. Okay, so this angle in here. All right, so I think cosine law would probably do it. Yeah. Okay. All right, so first thing I think I want to do is give you sort of a bird's eye view of ABC, just to avoid making that diagram more messy. So here's ABC, right? And then the midpoint is M, so that's M right there, I believe. And so I have called it X, right? So this is 60, this is 30. So just based on the whole 30, 60, 90 triangle thing, which everybody knows, the ratio of the sides are 2, 1, and root 3. So that means if one side is x, this side is x over 2, and this side is root 3 times x over 2. Yeah. Okay, so that helps. So now let's use the cosine law, and we're going to use it on that triangle DMC. So on triangle DMC, let's use the cosine law. All right, so here we go. So that means that DC squared is equal to DM squared plus MC squared minus 2 DM times MC times the cos of CMD, that angle. CMD, that angle. All right. Okay, so DC, I believe, was x. So that's x squared. DM, that's root 3x over 2. Yeah, root 3x over 2. MC, I believe, is the same thing. Root 3x over 2, all squared, of course. And then this DM and DC all by themselves. And then the cos of CMD, which is what we are trying to figure out. So I think that is the unknown. Okay, so let's do this now. X squared plus, what's that, 3 over 4? Yeah, 3 over 4, x squared. 3 over 4, x squared again. And this is going to be what? Minus 3x squared over 2, I believe. Yeah, and then cos CMD. Okay, the good news is that the x squared canceled everywhere, so we just left with 1. 3/4 plus 3/4 is 6 over 4, which is 3 over 2. And then we have minus 3 over 2 cos CMD. And then, let's see here. If I bring this 1 over, that'll be a half. This will be 3 over 2 cos CMD. And therefore, cos of CMD will be 3 over, hold on. 1 over 3. 1 over 3. Yeah, and that's it. So we got it. So that is B for number 12. Let R be the region in the complex plane consisting of all complex numbers Z that can be written as the sum of complex numbers Z1 and Z2, where Z1 lies on the segment with endpoints 3 and 4i, and Z2 has the magnitude at most 1. What integer is closest to the area of R? All right. So let's draw a diagram. So here we go. This is your real axis. And this is your imaginary axis. So let's see what we can do here. So Z1 lies in the segment between 3 and 4i. So 1, 2, 3. So this is 3. And then 4i, 1, 2, 3, 4i up here. Okay. All right. So there's a line, I guess, between those two. So let's just draw that line. And that is the story of Z1, basically. Z1 exists somewhere on this line. Okay. Z2 has a magnitude of at least 1. So that means that Z2, I guess I use a different color, it can extend from Z1. So first let me just draw in Z1. Like, for example, from the origin, if I drew that, that's a Z1 because it ends on that red line. Similarly, that's another example of Z1. It ends on that red line. And any such, Z1, as long as it ends on that red line. But Z2 has a magnitude of 1, and that's all they tell us. So that means that if you drew Z2, it could start from Z1 and go anywhere as long as it has a magnitude of 1. So for example, it could go like this, Z2, where that's a magnitude of 1. And so on, right? You can draw like this, that's z1, or and so on. I don't want to make the diagram too messy. But when you do draw all these possible z1s and then connect them, you're going to have a region like this, like that. And then over here, this is where it kind of becomes a semicircle, like this. And similarly over here, maybe I can just draw the semicircle in. And then I'll just draw, I guess, the region that, there you go, that region right there. I'll just make the semicircles a little bit more obvious. So exactly what the question said, z is the sum of z1 and z2. And z1 is on that red line. That is the segment between 3 and 4i. And z2 has a magnitude of 1. So with that limited information, we've drawn this region. And they want you to figure out the area of that region, which they have called R. Okay, to me that looks like a rectangle and two semicircles. The rectangle has dimensions, what, from here to here. It's 1 and 1, so its dimensions are 2. And then from here to here, that is the same as the red line, and the red line is 5, right? Because it's a Pythagorean. It's a 3, 4, 5 triangle, because this is a right angle. So there you go. That's 2 times 5 for that rectangular. And then you got two semicircles, which is the same as one circle. So it would be pi r squared. And r in this case is 1. Yeah, the radius of this semicircle. So it would be 1. So there you go. It would be 10 plus pi. And what do they want? The integer. Oh, they want an integer. So 10 plus 3.14, which is 13.14. So I guess the integer closest to that would be 13, which is choice A. What is the value of log 5 to the exponent 3 plus log 20 to the exponent 3 plus log 8 times log 0.25, where log denotes the base 10 logarithm? Okay, so let's make some substitutions here. Let's see what we can get. Okay, so I'm going to try to convert everything into something that matches. So, and then hopefully we can work with that expression. So let's start one at a time here. Let's start with this guy here, log of 5. Just log of 5. Well, they have told you that because they've not written a base, it's assumed that it's base 10, and that's a general sort of standard rule in logs. Okay, so then what do we do here? We have to manipulate this a little bit because I want everything to be the same. So what I'm going to do is I'm going to write that that 5 as 10 over 2. And when I do, then I can break this up into the log of 10 to the base 10 minus the log of 2 to the base 10. That's a log rule. Log 10 to the base 10 is just 1. And log 2 to the base 10, I'll just write log 2. And then the log of 2 I will call as A, like that. Okay, so then, therefore, this becomes 1 minus A all cubed. Yes. Okay, now let's do something similar to this guy. Let's see if we can get something similar. Log of 20, let's just go with log of 20 for now. So that's going to be the log of 20 to the base 10. Now, I'm going to break up that 20 into 10 times 2. And when I do, I get the log of 10 to the base 10 plus the log of 2 to the base 10 using basic log rules. This is, of course, 1. And then the log of 2 to the base 10, I'll just write as log 2. And the log 2, as before, I will call A. And therefore, that becomes 1 plus A. So this is 1 plus A, all to the base 3. Okay, so far so good, right? Not bad. Okay, so let's keep going here. Now we got to deal with this guy, the log of 8. The log of 8 is really just the log of 2 to the power of 3 to the base 10. And therefore, that's 3 times the log of 2 to the power of 10, or 3 times the log of 2. And since the log of 2 we have called A, this is 3A. So plus 3A. And then now finally we got that guy. And that is the log of 0.25, and that is the same as the log of a quarter, right? Yeah. So what is a quarter? That is the log of 2 to the minus 2, I think. Yeah. So then if you put that minus 2 up front, it becomes the negative 2 of the log of 2, and that's minus 2a. Yeah. So then there you go, minus 2a. And then what we do is we simply try to simplify that expression right there. So let's do that. All right, so we expand this all out, and when we do, we get 1 minus 3a plus 3a squared plus or minus, I believe, minus a cubed. And then plus 1 plus 3a plus 3a squared plus a to the power 3, and then minus 6a squared. Okay, collecting like terms, let's see here. That's gone, and I have 6a squared minus 6a squared plus 2, this and this. So therefore, it just gives me 2. Okay, so it all worked out at the end. It gave me a nice integer value, and that would be choice C for this question. The roots of the polynomial 10x cubed minus 39x squared plus 29x minus 6 are the height, length, and width of a rectangular box, a right rectangular prism. A new rectangular box is formed by lengthening each edge of the original box by 2 units. What is the volume of the new box? Okay, so this expression 10x cubed minus 39x squared plus 29x minus 6. Let's say the roots are R1, R2, and R3. They're saying that they're going to create a box with these height as the height, length, and width, but you are going to add 2 units to each of these. So the height will be R1 plus 2, the length will be R2 plus 2, and the width will be R3 plus 2. And this is the volume of this new box. So they want you to figure that out. Now, obviously, we will need to figure out the numerical values for R1, R2, or R3, or some combination of that. So first, what I'll do is I'll expand it a little bit. It won't make much sense, but it won't look like it'll help, but let's just expand it a little bit. 2R1, R2 plus 2R2, R3 plus 2R1, R3 plus 4R1 plus 4R2 plus 4R3 and plus 8. Okay, and then I'm going to group it a little bit. R1, R2, R3 plus 2 times R1, R2 plus R1, R3 plus R2, R3. Yeah, R1, R2, R1, R3, R2, R3. And then we got 4 times R1 plus R2 plus R3. And then we finally got that 8 left over. Okay, so that's about as far as I'm going to go there. Now, of course, some of you have already predicted this. You're going to use Vieta's. And Vieta's formula is sort of the heart of this question. Vieta's formula, there's many, but in this case, we're dealing with the cubic polynomial. So for a cubic polynomial of the form ax cubed bx squared plus cx plus d, Vieta's states the following. It states that the sum of the roots, which is r1 plus r2 plus r3, are equal to minus b over a. So in this case, since this is our polynomial, my minus b over a would be 39 over 10. Yes. It says the sum of the products, the Vieta's, which is r1 times r2 plus r1 times r3 plus r2 times r3, that, according to Vieta's, is c over a. And in my case, my c over a is 29 over 10. So 29 over 10, put that there. And then finally, the product of the roots, according to Vieta's, which in this case is r1 times r2 times r3, is minus d over a. And for my equation, that is 6 over 10. Got it? Okay, so I think we have everything we need. So this guy right here, we have as 6 over 10. You see how everything's going to fit now and it'll all work out. And then we have 2 times this, which according to Vietez, we have figured out as 29 over 10. And then we have 4 times this guy, which is the sum of the roots, which is 39 over 10. And then finally we have that plus 8. And when you add up all these numbers, you get a nice whole number, 30. And therefore, number 15 is D. A triangular number is a positive integer that can be expressed in the form Tn is equal to 1 plus 2 plus 3 dot 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 plus n for some positive integer n. The 3 smallest triangular numbers that are also perfect squares are T1, T8, and T49. What is the sum of the digits of the 4th smallest triangular number that is also a perfect square? So you guys know by now that this sum of consecutive integers can be written as n times n plus 1 over 2. It's a very famous formula, very helpful also. Now they're saying that we have some sort of scenario that this also is a perfect square. So I'll just call it m squared to represent a perfect square. All right, great. So that means one of two things. It means that either you have n over 2 times n plus 1 is m squared, or it means that n times n plus 1 over 2 is equal to m squared. Now you might say, well, isn't that the same thing? Yeah, it is, but I'm just grouping them into different categories. So either this is a perfect square, I'll just put PS for perfect square, and this is a perfect square, or this is a perfect square, or this is a perfect square, right? So there's lots of scenarios here, and we just have to fiddle around with this a little bit. Now, I'm just going to concentrate on two things. I'm going to concentrate on this guy and this guy. So what that tells me is that either n is a perfect square or n plus 1 is a perfect square. If n plus 1 is a perfect square, that means that a perfect square minus 1 is equal to n, right? If n plus 1 is equal to a perfect square, I just put the 1 on the other side. So what we can do is we can sort of test values of n that are either perfect squares or one less than a perfect square, right? For example, let me give an example. Like we are given the first ones, right? N is 1, or a perfect square would be. We have been given. Let's see here. Let's list them first. Let's give a sort of an idea. 1 squared, 2 squared would be 4, 3 squared is 9, 16 is the next perfect square, and then dot dot dot. Then we get 49, 7 squared, 64, and so on, right? I'm just going to list a few of these. 121, 144. These are all perfect squares. And remember, we're following this rule. N is a perfect square. And I'm going to test values of that. 169, 196, 225, 256, 289, and so on. But in addition to these, we can also use the fact that n could also be a perfect square minus 1. So it could also be perfect square minus 1 would be the values like 3, 8, 48, 63, dot dot dot, all the way up till 288, 255, and so on. Right? So what we have to do is plug these values into this equation and see if it gives me a perfect square. So it takes a little bit of math here. So and after you plug these numbers in, after some testing, you'll find that when you use this guy as the n and put it in here, you'll get 288 times 289 divided by 2, And that is equal to 41616, which is indeed a perfect square. It is 204 squared. And what they want is the sum of the digits of this guy. So the sum of the digits of that guy would be 4 plus 1 plus 6 plus 1 plus 6, which is equal to 10 plus 8, 18. And therefore, D is the answer to this question. Suppose A is a real number such that the equation A times sine x plus sine 2x is equal to sine 3x has more than one solution in the interval 0 to pi. The set of all such A that can be written in the form PQ is the union of QR, where P, Q, and R are real numbers with P less than Q less than R. What is P plus Q plus R? Well, we have the identity sine 2x. You guys remember that. 2 sine x cos x. And then you also have the sine 3x identity, lesser known, and that's sine of x is equal to 4 cos squared x minus 1. Okay, so let's put those in here, and off we go. So we're going to have A times sine x plus 2 sine x cos x, and that's equal to sine x 4 cos squared x minus 1. All right, so now we have A times 1 plus 2 cos x. All right, like that. And what I'm doing basically is I factored out the sine x and then got rid of it. So that's why it became 1 plus 2 cos x. And on this side, we're just left with this 4 cos squared x minus 1. All right, keep on going here. Let's put everything on one side. And when you do, we get 4 cos squared x minus 2a cos x minus, and then we'll just put this as 1 plus a. And that's going to be 0. So now it's a quadratic because we just use the quadratic equation to solve for cos x. And when you do, you get 2a plus or minus the square root of 2a squared minus 4 times 4 cos, 1 plus a all over 2 times 4. Okay, that's nice, I think. Okay, so let's see what this gives us. 2a plus or minus 4a squared minus or plus, let's see here. I think there'd be a minus 1 missing in here somewhere. Yeah, because this is, you gotta remember that's a minus 1. So this actually becomes 4a squared plus 16a plus 16. And then, of course, we got this whole 8 over there. So this is 2a plus or minus, and then this factors nicely. It's 2a plus 4 all squared. And then this becomes, we can put this over 4 now. This will become a plus or minus a plus 2, yeah. And then therefore this is going to be either a plus 1 over 2 or negative a half, and that is cos x. Okay. All right, we got it all the way down there. Now, if cos x, let's do the easier one first. If it's negative a half between the interval 0 and pi, which is what they gave me, and let's see if I remember that graph. It's like this, right? So if it's a negative a half between 0 and pi. Okay, so this is pi, right? So I guess the only choice is 2 pi over 3, which is 120 degrees. And then if cos x is this guy, which is a plus 1 over 2, and then again, x x is between 0 and pi. X is between 0 and pi. So, well, cos of x we know is between negative 1 and 1. That we know from this graph or also by memory. That means that this a plus 1 over 2 is also between negative 1 and 1. So that means that our range would be a is either -3 or 1. Yeah. That's our range also. Yeah. And then the other last scenario is if these two were equal. So if a plus 1 over 2 was actually equal to -1/2, and if that's the case, then a would be -2. All right, so let's put this all together now. So that means that a is an element of -3 to -2, and the union of -2 to 1. So I put these guys all together. -3 to -2 to -2 to -1. They want it written in that form. You see right here in the question, they want it written in that form, satisfying that inequality. And that's exactly what I did. So now this is the P, this is the Q, and this is the R. So P plus Q plus R, that's just going to be -3 -2 plus 1, which is -4. And -4 is choice A. Let TK be the transformation of the coordinate plane that the first rotates the plane k degrees counterclockwise around the origin and then reflects the plane across the y-axis. What is the least positive integer n such that performing the sequence of transformations t1 through tn returns the point 1, 0 back to itself? All right, now we need to figure out what is happening in this question. So let me just explain it with a little diagram. So let's say we start at 1, 0. Let's just use that point, might as well. And we are going to transform this somewhere. I don't know where, so let's just put it there. And we just kind of moved it from here to here by a certain number of degrees, let's just say theta. Then they're saying they're going to do this transformation. And what the transformation is it's called TK. And the first part of that is that you rotate it k degrees. So you're going to rotate it another k degrees, so this way. So from this point right here to this point right here. So for example, if it was T3, it would be 3 degrees. If it was T7, it would be 7 degrees, like that. And then the next part is that you reflect it across the y-axis. So if this is the y-axis, obviously, it would be reflected like a mirror image to that side. So it would end up here. So this is now your new point. Okay, so that's basically what it's saying. So I'm going to write it in terms of r theta, where this is like, since they're giving us 1, 0, I'm going to use sort of a unit circle situation. And theta is sort of representing the how many degrees it's rotating. And r is sort of the amount of distance, I guess, of this part. Okay, so the first move of this is a counterclockwise move by k degrees. So that would basically take it from theta to theta plus k. That's this part of that question. And then the next one is it reflects across the y-axis, right? So that would then make this go, if it was just r theta, it would basically be r 180 minus theta, if you're just doing that. But we are doing both this and this. So if we're doing both, we have to combine them. So if you combine them, that means that TK basically is a situation of R, and then you have to combine these. So it would be R and then 180 minus theta plus K. Right? Because first you are doing this guy right here, and then you'd have to subtract 180 minus whatever. So it would, a better way of writing it is theta, R theta plus K would basically be R of 180 minus this theta plus K. Like that, which is exactly what I wrote here. And this simplifies to R 180 minus theta minus K. And that's your TK. You got it? So let's extrapolate this now, because we have to do this numerous times. So our initial R is 1, 0. Our initial point, whatever. And then we have our T1. So T1 is when K is 1, right? So that means 1, 0 would then go to if you use this formula up here, right here, it would go to 180 minus theta, which is in this case is 0, minus K, which is 1. So 180 minus 1, which is 179. Got it? So now let's do this again. K equals 2 this time. Now we have to do T2. T2 is you're taking 179, and then you're taking it to here. So it would be 180 minus theta, which in this case is 179, minus K, which in this case is 2. So this gives me 1 and minus 1, right? Yeah. Okay, let's keep it going. K3, this is T3 this time. Now we have 1, negative 1, and this would basically be 180 minus 1, minus 3. So that looks like 181 minus 3, so 178. Okay, and then you just keep going here. I'll just do one more. K4 is this 178. So this is going to 180 minus 178 minus 4. And that looks to me like minus 2. So 1 minus 2. And if you extrapolate this, extrapolating, you basically get the following. That when you have a even value for this guy, for K, it becomes 1 minus n, like that. And you can verify that for these guys. And if it's an odd 2K minus 1, that kind of story, it becomes 180 minus K. So for example, when 2K minus 1 is 3, that meant that K was 2, and that's why we got 178. Okay? So what we want basically is this to be equal to 0, because we want 1, 0 to eventually go back down to 1, 0 again. So we want 180 minus K to be 0. That means we want K to be 180. If we want K to be 180, then that means that this guy would therefore be 2 times 180 minus 1, which is 359. So on T359, the 1, 0 would eventually go back to 1, 0 again. So that is 359, makes it choice A. Suppose that 13 cards numbered 1 through 13 are arranged in a row. The task is to pick them up numerically increasing order, working repeatedly from left to right. In the example below, cards 1, 2, 3 are picked up on the first pass, 4 and 5 on the second pass, 6 on the third pass, 7, 8, 9, 10 on the fourth pass, 11, 12, 13 on the fifth pass. For how many of the 13 factorial possible orderings of the cards will the 13 cards be picked up in exactly 2 passes? Okay, so let's talk about this before we jump right in. What do they mean by this 2 passes? Well, I'll give you an example. Let's say we have 1, 2, 3, and then 4, 5, and 6, like that. So what we're doing, I'm just giving you a small example. So what we're doing is we're going to pick up the cards, working from left to right in numerical order. So let's do the first pass. So the first pass, as we go through, we're going to pick up the 1, the 2, and the 3. So the 1, the 2, and the 3. And then what is left, we pick up in the second pass in numerical order. And in this case, it's 4, 5, and 6. And there we go. We picked up all the cards, and we did it in 2 passes. Now, the example they give here, they actually had to go through, I think, something like 5 passes. So the first pass, they pick up the 1, the 2, and the 3. And then they have to go through a second pass. In the second pass, they pick up the 4, the 5. And then the third pass, they pick up a 6. The fourth pass, they pick up the 7, the 8, the 9, the 10. And then finally, the fifth pass, they pick up the 11, the 12, the 13. So that's why it's 5 passes. So what they're saying is, if you take these numbers 1 to 13, of all the arrangements, which is 13 factorial, different arrangements, how many of those arrangements can you pick up these cards in just 2 passes? Okay, so hopefully that makes you understand the question. So let's work through with this. Now, let's say I have an example. Let's say I have the first 5 cards that I pick up in the first pass, So those numbers 1 through 5 are picked up in the first pass. Then, of course, the remaining numbers, which are 6 to 13, will be picked up in the second pass. Okay, this is just an example. So that means that in this case, my first pass ended with the 5, right? So I'm going to let that be sort of the important number that I'm going to use, and I'm going to illustrate it. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? Now the 1 through 5, we can put them in any order. So this first pass, we can put the 1 through 5 anywhere in here. So we have from 13 possible choices, we can choose 5. So this is the number of ways of putting those cards 1 through 5 along this 13 string pattern. So there's 13 choose 5 ways to place those 5 cards. So let's just choose one. Let's one way of doing it. Let's put the the 1 here, the 2 here, the 3 here, the 4 here, and the 5 here. Okay, this is just one of the 13 choose 5 ways. Now we get to the second pass. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now we've already put the 1 here, the 2 here, 3, 4, and 5. Now, how do we put the other numbers 6 to 13? There's only one way of doing that. If you want only 2 passes, second pass, they have to be put in numerical order. So that means that the 6 goes here, 7, 8, 9, 10, 11, 12, 13. So there's only one way of doing that. Got it? So I hope that makes sense. Now, here's the thing. You have to subtract 1 for this scenario, as it would give 1 pass. For example, you notice how up here I put the 1 here and the 2 here and 3 here and 4 here and 5 here, right? Well, one of the many ways of putting those first 5 is to put them in the first 5, like that. And then 6 through 7 would go here. Now that is a problem because this only involves 1 pass. If you pick up the cards, you could do it all in 1 pass. So this one has to be eliminated from our total number. You got it? So similarly, for all values of k, it would be 13 choose k up here. Okay, and then you'd have just one way of doing it down there, and then you have to subtract this scenario, because this scenario would give you one pass. All right, so let's do that. And also, you have to remember that you are only looking at values of k between 1 and 12. Because if k equals 13, then you would only get one pass. You would only basically get, you would get this scenario. So that's another thing we have to figure out or take into consideration. So for each value, for each k value, the number of ways is 13 choose k from up here. This is just 1, so that's not going to make a difference. You can put it in if you want, but you don't need to. And then subtract this one over here, because we don't want that one. So essentially it becomes a summation type of scenario where k is going from 1 to 12, and you're calculating 13 choose k minus 1 for each of those. And I think most of you are pretty familiar with summation notation. So this would basically be 13 choose k for k equals 1 through 12, and then this will be a minus 12. We can put that out there. And then it just becomes 13 choose 1 plus 13 choose 2 plus 13 choose 3 plus ... You guys get the point, all the way till 13 choose 12. And then don't forget that minus 12. And then these numbers, I crunched them out. 13, 78, 286, 715, 1287, 1716, 1716 again, 1287, 715, 286, 78, 13, and then don't forget that minus 12. And when you calculate this, it's 8178. And 8178 is choice D for this question number 22. Problem number 23. Isosceles trapezoid ABCD has parallel sides AD and BC with BC less than AD, AB equals CD. There is a point P in the plane such that PA is 1, PB is 2, PC is 3, PD is 4. What is BC over AD? Okay, so let's first draw a diagram. And let's see what we can show on a coordinate grid. So I'm going to put this isosceles triangle on a coordinate grid, or isosceles trapezoid, I should say, and try to illustrate how we can work with this question. And let me label it. So we have A, B, C, and D. And then for each of these, I will give it coordinates. So A, I will call x1, y1, like that. And then B will be, B is x2, y2. C will have the same y coordinate, but it'll have a different x coordinate. And then D will have the same y coordinate as A, but it will definitely have a different x coordinate. So I think that's the labeling. And I've got to stick my, somewhere in there I've got to put in the P, right? So I'm not really sure where. I'll just put the P here. And this will be P. And then of course I've got to join those like that. And they tell me that those numbers are, what are they? P to A is 1, PB is 2, PC is 3, and PD is 4. Okay. All right, so pretty decent diagram, not drawn exactly to scale, but it's okay. And we eventually want to figure out BC over AD, okay? So there's lots of ways of doing this question. The system I liked the best is to draw circles with a P being the center. And if P is the center, then that will definitely help. And the key in this question is to draw the P where the origin is. And I think that was what I should have done initially, but that's okay. I can do it now. So that's really important, actually. Okay, so now let's draw the circles. Now, B is a point on the circle. So if we were to draw a circle where P is the center and B is a point, the circle would look something like this, like that. Now I'm not gonna draw the whole circle in because it would make it confusing. And then same thing with A, it would make the circle look something like this. There would be a circle kind of like that. And then similarly, there'd be a circle kind of like this, and then a circle like that with D. Okay, so let's draw the equations now. For the circle with radius 1, it would be x1 squared plus y1 squared is equal to 1 squared. And that's equation 1. For the circle with radius 2, very similarly, it would be x2 squared plus y2 squared is equal to 2 squared. And the circle with radius 3 is x3 squared plus y2 squared is equal to 3 squared. And finally, the circle with radius 4 is x4 squared plus y1 squared is equal to 4 squared. And that's equation 4. All right, now one more thing is that since this is an isosceles trapezoid, if we were to take the midpoints of BC and AD, they would be the same. So if this is approximately the midpoint right here, and we took the midpoint of AD, they would essentially have the same x-coordinate. So midpoint formula, you can easily do x4 plus x1 divided by 2. That's going to give you this guy right here. And then that's going to be the same as this one, which is calculated with x3 plus x2 over 2, like that. So then you just get rid of the 2's, and therefore x4 plus x1 is equal to x3 plus x2. And this can be our equation 5, which hopefully we'll use later on. Okay, so now let's work with this. Let's look at these equations. The first one I want to use is equation 3, and from that I'll subtract equation 2. When I do, I get x3 squared minus x2 squared is equal to 5. And then I'll take equation 4 and subtract from it equation 1. And when I do that, I get x4 squared minus x1 squared is equal to 15. All right, so I think we're getting here somewhere, at least. And then we'll divide these two equations. So x3 squared minus x2 squared over x4 squared minus x1 squared is equal to 5 over 15. And let's factor this now. So x3 minus x2, x3 plus x2, all over x4 minus x1 times x4 plus x1, and that is equal to 1 over 3. And then let's see here, we can make this substitution now. x3 plus x2 is actually equal to x4 plus x1. So this part stays the same, but this x3 plus x2, I can put x4 plus x1. And that will help us because it'll allow us to cancel stuff out like this. So the good news is now that this cancels with this, and all you're left with is x3 minus x2 over x4 minus x1. And that is 1/3. Now, x3 minus x2, I'll write it up here. x3 minus x2 over x4 minus x1 is equal to 1 over 3. Now, go back to the diagram. x3 minus x2 is actually the distance from B to C. And x4 minus x1 is the distance from A to D. And in a very interesting way, we got exactly what they wanted. they wanted us to figure out BC over AD, and that's what we got. We got 1/3. So there you go. The answer to this is B.